So, shall we start? Hi, everybody. So, we ended up talking about the challenge of computing loss when we don't know the segmentation. So, do you remember what was the key problem? So, we talked about this particular example where we have, say, for example, a bunch of numbers. And what we want to do, we want to classify what's written on the text, right? We just want to give the image into a neural network, and it's going to tell us 2, 3, 2, 4, 1. So it's going to just get it and then write us this out. Let's just go further. Yeah, something like this. So we give it to a neural network, and it's going to just give us as the output, oh, where is it? Maybe like this, 2, 3, 2, 4, 1. And we talked about this that, I mean, in the core case, like when we have perfect segments, it's a simple task with a convolutional neural network because you can give every single image to your CNN, and it's going to give you, classify for you the number, right? But the issue is that you're not dealing with a single number. You deal with a sequence of numbers on your image. And you don't really know how exactly you're going to segment this because you just have the text written, right? So if you do that, we typically deal with such sort of segmentation, right? And this particular problem that we talked is a very perfect problem for RNN because we have a sequence of data. The classification problem itself, like looking at a handwritten number and classifying it as a digit, it's not a hard thing. It's actually an easy thing. So you can do it with a simple neural network. But the challenge that you have is that you don't have just one single image of a one digit, right? You have a sequence of digits in your image. So it's a kind of sequential problem. Clear? And then RNN is perfect. So maybe you have trained CNN, and then you take the idea we started chapter 6 with, and then you just turn it into an RNN, and it's going to work for you. But when you do the segmentation, you end up with such a sort of segmentation, usually, right? And then in that case, we have this problem, which we call it the correspondence problem, meaning that you have your sequence, for example, X1 is the very first frame or very first segment of your image. And this is, I mean, practically no digits, right? It's a tiny part of 2, meaning that, I mean, you don't expect anyone understand what it is, right? It just needs to look at the next segments like it should be over with all the segments till it understands 2, right? And you potentially have a very long input, which is the whole segments, but that long input is corresponding to one particular sequence of labels again, but that sequence of labels is shorter than your input sequence. Clear? So this is the problem, and there are two key issues here. We talked about this last time. The first point is that where should we put that label sequence, right? So this is the very basic form, or very, so say, one of the first problems that we could have in seg-to-seg problem. So, or sequence-to-sequence problem. We're going to talk about this next session in chapter 7. But in general, what we are seeing here is that we have this model, which is our neural network. For example, this is a RNN. And this guy is now getting one sequence as input, right? And this sequence is the one that you have, xt, right? So xt is x1, x2 till xt, right? And then at the output, you are also seeing another sequence. That sequence is the sequence of your labels. It's vk. And I'm showing it by k because the time index is now different, right? So I give it like a sequence of 100 different frames, 100 different segments of my image. Then at the output, I get only 10 digits, right? Because that 100 segments correspond to 10 digits written there, right? Okay? Now the question here is, the first question is, okay, say I have those 10 different digits. I do know. I mean, this is training data set. I do have the input sequence, which is segments of my image. I do have the output sequence, or the sequence of labels, which are the labels corresponding to that text. But then, where should I put this first digit to? Should I put it after the first segment, or after the second segment, or so on, right? In many applications, in many cases, we don't really know where we should put it here. Where it should, put the first digit, second digit, and so on. This is the first one. And secondly, say we figured it out, right? So there are lots of guys remaining without any label. What should we do with them? Should we simply ignore them? Or should we consider them when we are doing the training? It's another question, right? So this is what we call it one-to-one correspondence problem. So in general, in correspondence problem, we have two sequences. Every single sample that you have inside your data set consists of two sequences. One of the sequences is the input sequence, which is of length t. One of them is the output sequence is of length k, and that k is smaller than t, and you don't really have any predefined connection between the entries inside the input sequence and output sequence. Okay? Clear? So input sequence is what I show it by xt here. So it could be of length 100, and then the output sequence could be of length 10, right? And you don't know, like the first entry in this output corresponds to which entry, or you should somehow correspond it to what you see at the output of your neural network after which time, right? Clear? Okay. So this is the one-to-one correspondence problem, as I told you, and it's going to show up in many applications. This was one of the bottlenecks that people, again, struggled to get into seg-to-seg problems. So when CTC came and it worked, everybody said, yeah, thumbs up, it's going to work. We could now get a complete sequence, turn it into a complete sequence. Okay? And those of you who might remember, like early days when neural networks were introduced, many people were saying like, yeah, well, they are intelligent, they can do very good classifications, but at the end, when you get into a human type behavior, which really needs to know this kind of behavior, they are incapable because they cannot do it, right? But CTC was a kind of turning point, which made it also possible. So classical application is speech recognition. So when I'm talking and you want to label my talk, maybe I talk 1 hour, I'm talking only about 2 topics, right? And then you want to label, I mean, up to, I don't know, minute 54, I'm talking about first topic, and from then on till the end, I'm talking about the second topic, for example, right? And then you don't really know, I mean, when you get my voice as a kind of input, it's going to be a very, very long sequence of many frames, right? And then you don't really know where I ended the first topic. So you don't know where you should put that label of the first topic. And the second label, you don't know where to put it again, all right? This is one issue. Another case is like text recognition, so the example that I showed you, and I'm pretty sure that you can come up with lots of other applications when you have this kind of challenge, okay? So here now, at this point, this is what we call it usually a kind of advanced topics in deep learning. You do all know how deep neural networks work. You do know how to train them. The challenge is that when you want to write down the things, the training loop, or you want to test them or use them, you don't really know how to define the components. What is the component that you cannot define here? The loss. Because I give you the input, my audio file. I give you the label, the 2 topics, right? And then you don't know how to get these 2 and compute the loss out of it, right? You do know that if you can compute loss, then everything is done, right? But you don't know how to do it. And this is what we want to do it here. So this is one sample of advanced topics, right? So there are going to be lots of other challenges. So we're going to mention in the remaining time a couple of them. But everything that I explained here, or from now on, or if you see, they're all in the terminology that you have learned up to this point. Okay? So you can simply follow everything. Okay? Great. So now let's just write it down a bit in form of a mathematical problem. So what we have here, We have a sequence of data as the input sequence, which is my audio file, which is the image, the segments of the text image. And then it is of length t, so x1 to xt. And then this sequence is labeled with another sequence. And that sequence is a sequence of labels, v1 to vk. And that k is smaller than t. Okay? Now, any idea what is, for example, this v? What kind of vector that is? I mean, in the image case, we were just the digit recognition, text recognition example. So these x's are pixel vectors, right? You agree? Because every single x1 is like here. x1, say for example, is this first frame, okay? So if I take this first part between the first two dashes, yeah, this part of the image, I can show it in terms of lots of pixels, right? And I put them next to each other, it's going to be a long vector of pixels. This is my first frame. And then I go for the next segment, this is going to be the next frame, and so on, right? So when I say x1 to xt, this x1 is basically the pixels of the first frame, right? Clear? Now, what is this v1, for example? It's 2, right? But this is, if it is an output of your neural network, it's going to be 100 representation of 2, right? So, sorry. If, for example, in the example I told you that we do know that in the text we have only digits 1, 2, 3, 4, right? So this v1 should be one vector, one hot vector of length 4, right? So if it is 2, it's going to be 0, 1, 0, 0. Correct? Yeah? And now, we had 5 digits. So we're going to have v1 till v5. But we might have 100 segments, right? 100 frames in our input. So everybody got what are these notations here? Yeah? OK. So we got x, we got v, and then k is smaller than t. This is the point. And now what we want to do, we want to basically understand how we can get this v and out of it compute some loss function, okay, or loss value. So let's just break it down first. Say I have given this x into my neural network, and that neural network is an RNN. Okay? What do? I'm going to start with an initial state. I'm going to give x1 to it. It's going to give me some hidden state, right? Out of that hidden state, I can compute the first output, right? Correct? Then I go for the next time interval. I'm going to give the next hidden state, the next input. Then I can compute the next output again. And I go on in time, right? Correct? So when I have t different time intervals inside my input, I'm going to have t different time intervals at my output, right? But not all of them are meaningful outputs for me, right? Because I have 100 outputs. Out of them, 5 should be those digits, right? Clear? Everybody's following? Yeah.
So other than the 5 meaningful output, what will be the other output?
Yeah, this is what we want to figure out. We want to understand what they are. I mean, they are not necessarily useful things, but sometimes you can make use of them.
And more importantly, we need to distinguish that to the real useful output, because we only want 5 digits to be recognized.
Yes, we want 5 digits to be recognized, but 2 questions. First of all, where should we read the first digit? Yeah, where in the time sequence? Yeah, this is the first one. The second one is that say I should read it on index 5, okay, or index 10. Like after the 10 outputs of my RNN, I should look at that and see what is the class of the output to say this is the first digit, okay? But then when I want to do training, what should I do with the output of all of these previous time steps, right? Because I can use them to train my output layer, correct? So how can I use them in my loss? It's not yet clear. Yeah? You got it? Great. So now what we want to do, we want to be able to define a loss function. And this loss function should have a couple of properties. The first thing that we need is that it's going to get this, 2 sequences. And these sequences are of different lengths, but it should compute some scalar loss out of it, right? So they are not one-to-one mappings, so there is no one-to-one correspondence here, but it should be able to compute a loss out of it. This is the first thing. The other thing that we want to be able to just differentiate this one. We want to be able to compute the gradient of this loss with respect to all outputs. Clear? Because at the end of the day, I want to be able to compute the gradient of this guy with respect to every single output that I have, and I use it in my chain rule and backpropagation algorithm to compute a sort of update value for my weights, right? I need these. I mean, when we started in RNN, I told you that, like, take it from my side that we can compute that, right? Now we want to make it clear how exactly we can do it. Okay? Good, great. Now, this is one thing that we want to do. So we want to be able to use those, different sequences to do the training, compute loss, and then do the training. The other thing is that we want to be able to use it for invariance. And I have used this term invariance a couple of times in the lecture, but do you get what do I mean by invariance? You don't get it, right? So say I got a new, it's nothing, you do know it. If I get a neural network and I train it, okay? I train it, I test it, everything works fine. The test accuracy is 99%, perfect. I'm going to take it, I put it in my pocket and go, right? And then one day I see something that is the input of this neural network, right? So what is the use of that neural network in my pocket? I can take it out, give it as input, and see what is the output, right? I look at the image, give it to my neural network, see what is the class, right? This is what we call it invariance. Okay? So you got your trained neural network. Now you should be able to use this neural network to just predict what is whatever output you want, right? In the classical CNN or RNN or whatever we have discussed up to this point, that invariance is quite easy. Because, for example, if I have a classification problem, then if I give an image to my trained neural network, it's going to give me a vector of probabilities, right? And you do know how to infer the correct or the predicted class out of this output, right? You're going to look at the guy who is largest. You say, this is the most probable class, so this is the class that I'm going to infer, right? But what about this case? Because say I have trained my RNN on different text images, right? All of those text images, say I have made them into 100 segments. But maybe someone writes very small, and within that tiny part of image, they have written, 10 numbers, 10 digits. One other guy writes very, big, and then there is only 4 digits there, right? So in your training data set, you have multiple samples. Each of them is somehow mapped into one sequence, which is of different length, right? So say you did the training and it's over. Now you just get another text and you give it to your neural network. You look at the output, right? Your neural network is going to give you at every single time one particular output, right? And then the question is when you should decide to read it and how you should read it. Clear? You got what is the challenge? So it's not only about training, because training is, of course, an issue here because you want to compute the loss. But even when you are over with training, you want to always be clear how you are going to use it after you do the training. Because you might train it very well on that data set that you have, but at the end of the day, when you just give a new image, a new text into your neural network, you are not clear where I should read the output, right? So these two things are the things that we want to answer, and this is the whole idea of segmentation about, okay? And this is, as I told you, one of the first problems showed up in terms of sequence-to-sequence modeling. Like you get a sequence and then you convert it to another sequence, okay? Great. So now let's just start with simple cases, okay? The first case that we have is the case of perfectly segmented scenario. So what does it mean? It means that like the image that you are giving to your neural network is perfectly segmented so that for every single time interval you have a label. So what kind of problems could rise up here? One of them is this many-to-many case when type 1, right? You have input at every single time interval, and you have a corresponding label at every single time interval. That is quite easy, right? This is what we usually thought of when we were training RNN. Because then I have my output y1, I can compare it to v1, and then I add it at the loss to the next time, and so on, right? That's easy, correct? Another case that could be like this is the case of one-to-many. Why? Because in this one-to-many case, I have one input, it's, for example, image, and then the output is going to be a sequence, yeah? And that sequence is, for example, the caption of that image, if you remember, right? Again, here there is no problem. Why? Because at every single time interval that I am just generating one output, I have the corresponding label, right? I still can compute the loss, I still can do the inference, so there is no problem, right? So I don't care about not having input at these time intervals because I always can think of them as empty inputs. And input does not show up in my training nor in my inference, right? So new image, I give it to my neural network, I leave the input empty, and it's going to generate the sequence of the caption, right? No challenge in that respect. So this is the case where we say perfect, the output sequence is perfectly segmented. And in that case, defining the loss is not an issue at all, right? So for every single time interval, I'm going to compare my output to the true label, and then I just add them up, right? And then it's going to be the total loss, and then out of that, I can just do the training or the inference, right? For training, I have no problem because I can compute the gradient with respect to every single output. If I want to compute this guy, this is basically the gradient of that particular loss, right? Because yt only show up in my loss computation at time t, nowhere else, right? And I can always compute that gradient. No worries in that respect. And of course, for inference, you also have no problem again. Obvious? Because every single output at every single time that you see when you give your new input to your model after training is corresponding to one label, right? So if I give one, say I had a bunch of images, and I am training my RNN to do image captioning. It means that I had maybe an image of a cat, and then the sample caption was, this is a cat. I had image of a dog, and the caption was, it is a cute dog, so on, right? And then I just train my RNN. Now I give an image of a tree. And then it's going to write down maybe this is the image of a green tree in nice weather, I don't know, and blah, blah, right? I don't care. Every single time I'm getting one word out of my neural network, I don't have any problem with inference, right? Every time I'm going to read the output. Clear? So there is no problem in that respect. Every single output is corresponding to one label. And here I'm showing with v hat. And do you know why I show it with v hat? It's not the real, it's the predicted one, correct? So here I'm doing inference, meaning that I get a new data, new x, and I give it, I don't know what is the true label. I'm just looking at my output, and out of that I am just inferring what is the true label, right? Or predicting what is the label, right? So I'm getting a bunch of predictions at every time, everything is okay, right? For example, if we think of the example we had already, the text recognition example. So I told you we have 4 different possible cases, right? 1, 2, 3, or 4, right? And then true labels are one hot, right? But the output of your neural network is going to look like this, right? So it's going to be a vector of probability at every single time. But you would say, if you get at one time this, then you're going to say this is corresponding to 2 because the second entry is the largest one, correct? Yeah? So your v hat at this point, if this is your yt, then your v hat t going to be 2, correct? Or the one hot vector. I mean, it depends on how you want to think of it. Clear? So training inference is easy in this case. I mean, pretty much we don't need to do any modification. Correct? Okay, great. So next thing. The next thing is when we have something, I call it known segmentation or known segments. And what is this known segmentation? It is basically what you had as many to one label. So in this case, one example of this one is, for example, when you just listen to the whole audio, and at the end of that audio, you want to just say, what is this audio about, right? So your whole sequence as input has only one label, right? So this could be potentially one case where really every single sequence that you have in your data set is only labeled with one label. This is one case. But there is also another case where you really know the segments, right? So I'm going to talk, and I'm not talking about one topic, I'm talking about 10 topics. But when you want to save my audio in your data set, you stop at the end of my first topic, you cut it, you would say, okay, this part of the sequence is labeled with topic 1, you put it in the data set, then you listen to the rest of my talk, then you just cut it again, you label it, and so on, right? So you either really have a sequence which has only one label, or you have a sequence which has a label once upon a time, but you really know the segment, right? Then you can just break it down into a list of sequences, each of them having only one label, right? This is why I call it noun segments. Both of the cases could happen, right? Now, at the end of the day, either of these cases, whether you really have only one label or you just break it down into subsequences and then you label every single subsequence with only one label, then you're going to see such a problem, right? So it's many inputs, one complete sequence, and then it's going to be labeled with only one label. And that label could potentially happen at very, very end, right? Clear? Yeah?
And the length of T, the length of this input sequence could be anything.
Anything, yes, yes.
So this can be the solution to our problem, right?
But very easy case of it, right? Because in our problem, we don't think of having only one label, right?
Yeah, but then it's known segments.
But what if you don't know the segments? That is the main challenge.
But we can human label the segments.
Yes, but think of trying to get a bunch of handwritten images and making it into a data set, a training data set. So you want to go over all the handwritten text and segment it? Is it possible for you?
It would require a lot of work.
A lot of work, but this is not what you want from an automated system, right? You're designing the whole intelligent system to work fine, right?
Yeah, but before we train the model, we do the human labeling.
Yes, but this should be feasible, right? I mean, for MNIST data set, it's feasible. But for that task, it's not feasible. And given that you do that, what about inference? How do you want to read the output? Again, you don't know the segments. Here, we assume that we really do know that every sequence going to our neural network is just going to be labeled with one label, right? Then that is easy, right? Because, for example, it might be a kind of competition. Everybody talks 5 minutes, and then you want to just different topics, and then you have only audios of single topic talks, right? Then this makes sense to consider such a model. Right. But if someone is talking the whole time, and then
there's multiple outputs.
Yes, multiple outputs, and then you really don't know where to start to cut that, right? Yeah. So knowing the segment is a kind of challenge. If we did know the segments, there was no issue. I mean, we could just finish it here very quickly. Yes, so very easy. You're going to see this. Yes.
So even if we know where to read output, what do we do with the rest of the data in terms of training?
Yeah, I'm gonna talk about this right now. Yeah. Okay. Yeah, but this is a kind of challenge, right? But here it's not a big challenge, but for later cases, it's going to be a challenge. Okay. So now everybody's clear about this one, this case. So one sequence input, only one label as the output, right? Okay. So now in this case, you might go for the naive approach. This is what you have in your assignment. You get the whole image of the MNIST, the whole image is a sequence of, pixels, and then you look at everything with one label, and then you train it only with looking at that one label. For that particular example, you're going to see that everything works fine. So this naive approach is going to work fine. But what is the naive approach? The naive approach is going to say, okay, I'm going to wait till the whole sequence is out, yeah? And then I'm going to look only at the last entry inside my output sequence, meaning that I don't really care about y1 to yt-1, right? It's not going to harm that much, right? Because I start from yt, and then when I want to train, I'm going to just backpropagate all the way to the beginning, right? So anything below the output layer is going to get trained well, right? The only thing that is not going to get trained very well is the output, right? Output layer. Because for output layer, we have only this guy, right? To train with. Clear? Yes?
For example, we consider it's like a sequence of numbers.
X. You mean X?
All PX, for example, there's going to be 2, 3, 6, 7, and something like that. For example, 5 digits.
Is okay.
Yeah. And when we just get one label, what is this label? Is it just 1, 2, or 3?
Yeah, it depends on your problem. Say, for example, you do know that the image that you have is only one digit. So there is just one digit written in that image, okay? Then what you're going to do, these X's are a part of your image, right? So for example, the assignment that you have is like this. So you look at your MNIST image. So this is your MNIST image. And this is of this form, right? So it's 28 by 28, correct? But then you're going to say, okay, this is the first frame, this is the next frame, and so on till the last frame, okay? Now, you're going to make your sequence, so it's going to be x1. x1 is just a part of your image, right? x2 is another part, the second row, and so on till you get into xt, the last row here, right? And then when you're over, you say, okay, this guy corresponds to label, I don't know. If it is written here 2, then you're going to say the label is 2. You get it?
Okay, yeah, but we start this problem with the segmentation, which was a sequence of a number. And
Yeah, this is again a segmentation, right? I'm reading the first part, the top part of image, then the second top part of image, and so on.
It's like our example, it was 5 digits.
Yeah, but I told you that here I do know the segment. So what I'm assuming right now is that in my whole image, there is only one digit. Yeah? So it's only written something like this. Yeah, somebody has written like. And I'm reading every single part of it. So every single of it is one of the entries in my axis. This is x1, x2, and so on till the end, right? And then at xt, when it's over, then I do know that the label is 2, right?
But if we know the segment, so what's
The benefit of using that RNN? Because this image could be of different length, right? I can write 2 in this form. You may write it down like this, and one other person might write it down like this, right? And then you want to be able to give all of those images and classify all of them as 2, right? So then you are dealing with sequences, not simple image. If you use simply just CNN, then each of them should be just given to a different CNN, right? Yeah. But with RNN, you don't need. Yeah.
So here the T is not known, the capital. Yeah?
No, it's not fixed. You can change it. Like in your data set, you could have different sequences of different lengths. Yeah. Clear? Okay. So now, if I only have one label, as I told you, the most naive approach that I can do is that, okay, I'm going to wait for everything to be out, and then I take the last output, I'm going to compare it to my label, and I compute the loss. So I'm going to put the loss to be the loss between YT and the label, right? And I'm going to train my neural network based on that, okay? But then, if in future I want to use this neural network to just label or classify one input, when does this neural network talk? When the time is over, right? So this is here you don't have any problem because you do have the loss, you can compute the loss, and then you can compute the gradient simply because the gradient with respect to the outputs, if this is the last output, the gradient is going to be the gradient of that loss function. If it is any other output, it's going to be simply 0, right? Because they are not showing up in your loss computation, correct? So you can do this, and of course you can do the inference, but this neural network is quite dumb because it needs to wait to see the whole image and then tell you it's number 2, right? Digit 2. But any human being could maybe here start to say this is 2, right? You don't really need to see all the tail up to the till end, right? After a couple of frames, couple of segments, you start to see this is 2, right? Clear? So this is going to work. As I told you, you're going to do this for MNIST in your assignment. But do you have any better idea? Can I make it a bit smarter?
Can't we train it? Can't you have like different weights for the different layers, and the weight converts to 1 from the end? So we train a little bit the other layers. So for example, if we are in the first layer before the end, it will train. So
By layer, you mean time interval.
Yes,
time interval. Yeah, this is correct. Yeah, this is exactly what we do. So if I want to just make it a bit more smart, okay, I'm gonna make it like it's gonna talk to me before it even see the image, right? This is the most smart creature you could think of, right? So you have number 2. Before it starts to go over it, like it sees only a single part of it, it tells you 2, right? If you want to do that, then you can just take that label and copy it on every single time step, correct? So what I can say, okay, after interval 1, I would like my RNN say 2. After interval 2, I want it to say 2, and so on till the very end, correct? So I get this label 2 and copy it on every single output of this sequence because this whole sequence has label 2, right? So I don't need it to be that dumb to wait for the very last segment, part of the sequence. I would make it extremely smart. It's going to just start saying 2, starting from very, very beginning. Okay? And then in this case, you again can compute the loss easily. So every single output that you get, you compare it to the particular output that you do have. The particular label that you do have, and then you just sum it up. You can simply add it up, and then you can simply compute the gradient. But if we do this, there is a bit of risk. Do you have any idea what could be the risk?
Yeah,
right?
I kind of before you even said the risk, I kind of feel this is problematic because, like you said, if you only give the very first frame, like where you draw that part. And you like the output layer to predict that is a 2. There is a problem because to me, maybe that is a 7 for example, because we have a
Yes.
So we train the output layer a little bit too early.
Exactly.
We need the whole thing.
Exactly. So this is correct. If you just go exactly like this, you are not necessarily making it very smart. It could be that you start to learn labels from unrelated, irrelevant input, right? And this is going to make your neural network not really smart, but rather random, right? So it's not the best idea ever, right? So what we could say in general, we could say, okay, maybe here is not a good idea, but here maybe this slowly starts to understand it's 2, right? Maybe here it understands more, and maybe here it actually should understand this is 2, right? So the better idea that you can do is that you would say, okay, at every single time, I'm going to get the label that I have and compare my output. I compute the loss, but I'm not going to give it with the same weight, right? I give it a weight, correct? And then potentially that weight, this guy could be very small when we are starting, because at the beginning it shouldn't know anything, right? Potentially 0, right? It's going to be 0 up to some point, and it gradually starts to increase to 1, right? So it's going to get 1, and then somehow it's going to get exactly 1 when the sequence is over, because at that point your neural network should know what is the label, right? Clear? So you could get these kind of weights. In general, you can even learn the weight, right? Because that weight really depends on your data. For this image, maybe this weight should be close to 1 after this segment, right? For one other image, maybe it should be 1 quite later, right? So you cannot really say. It depends on your data. And then you potentially could look at those W's as a bunch of parameters that you want to learn. And again, you learn them. Yeah? Everybody's clear? OK, great. So in this case, if you do that, then computing the gradient is, again, easy for you, because you can compute the gradient with respect to every single yt, because basically there is only one term depending on that yt, and this is going to be of this form with the corresponding weight. Yeah? So this is the classical approach. As I told you, the naive approach is going to work. It's going to just make your neural network a bit slow, right? And then for the example of MNIST that you had in the assignment, it's not an issue, right? Because you anyway want to wait till the end of the image, correct? But if it is a kind of online application, it might be a better idea to just wait it. OK? Great. So for invariance, what if you just train that neural network, and now you want to use it to just classify one image, right? So you got lots of digits, and then each of them is written with one length, and you train your neural network to look at all of those images and give you the number, the digit inside the image. Now, if you give a new image into it, what should you do? When do you read the output? At the end, this is one option. There are also other options. All of them, what they do, they're going to look at the whole output sequence, and they convert it into one label. That is, again, easy. You said at the end that is correct. This is one possible case, but there is also better cases. Like I can look at every single time interval output, and I use them to classify, right? And then I take the majority vote. OK? Maybe here at the beginning, it's unclear. Instead of 2, it classifies it as 7, right? But it's not going to happen later on, right? So if I have a very long sequence, it's going to be 7, 7, 2, 2, 2, 2, 2, 2, 2, like this, right? And then I'm going to look at the whole outputs, and I say, OK, most of them are 2, so I'm going to classify it as 2, right? This is alternative approach, majority vote, right? But you can come up with other approaches as well. Maybe you would say, I'm going to use the weights, right? So I'm going to look at the outputs, and then how much I should take every single output seriously. It depends on its weight, right? For example, if the weight for very first output is 0, it means that I shouldn't take it seriously, because that is there is no real information in that, right? So you can do lots of crazy things with that. It totally depends on you and the application that you are doing. But at the end of the day, you see the whole sequence, and you convert it into one label, which is a doable thing, right? Clear? So, but the whole challenge starts when we have really unknown segments. Yeah? This is the problem that we started with. Yeah? And this is the most general case. So what is it here? I have the sequence, and I have one sequence at the output, and they are not of the same length. And I really don't know this V1 belongs to which part of the sequence, right? So I really don't know whether V1 should be known at the second time interval or third time interval, or earlier or later, yes? And sometimes there is no even clear answer to that, right? Because you cannot say, when should your neural network start to understand this is 2, right? Maybe I say at this point, or you say no, at this point, right? Sometimes there is no even a clear answer to that, okay? So now here is the challenge, and the whole issue is that we want to be able to, as I told you, compute the loss, and also we want to be able to infer from the output after the training, okay? Now, as I said a couple of times, this is one of the very first problems in seg-to-seg models, sequence-to-sequence models, and then we are going to talk about it in more details. I mean, the more interesting part is going to come next Tuesday when we start with chapter 7, okay? Now, let me now give you one particular example, this example of 1-to-1. And this is, I'm going to stick to this example for the rest of this part because it's going to make it like easier to follow the details, okay? So say I have this input 1-to-1, okay? It means that I have one image, and the image looks like this. The image looks 1-to-1. And then, when I wanted, this was in one piece of paper or something, right? And then I got it and segmented it into 5 segments, 5 frames, right? So it is frame 1, frame 2, frame 3, frame 4, and frame 5, right? Okay? And now, when this guy is x1 here, right? This is x2, x3, x4, x5. And what are the labels? First of all, what is k? The capital K? 3, great. And what is v1? 1. What is v2?
2.
What is v3?
1.
Great. Okay? So you got it, right? So now, the question is, when should I read the first one? Well, maybe you would say here, right? For this one. What about second one? Maybe it's here, right? And what about the last one? Maybe it's here. Yeah? But who knows? Yeah? You cannot say for sure, right? Great. So in this case, you have different, you really don't know where to put those labels. So this is one possible combination. Yeah? Another possible combination is that maybe the very first one, maybe instead of this guy was really here, right? So it was exactly written here. And then your label was really at this point 1, right? So it could be a different form of segmentation of your input, right? And we don't really know, as I told you, we don't really know where to put those labels when we want to train. And if I give a new input, I really don't know where I should read, right? Because one might write in this form, one might take this one closer, yeah? And the other point is that sometimes, as I said, there is no concrete answer, right? So if I just play with these framing, it could be the case where the half of 2 is there, and I don't really know where I should. Even if I look at it, I cannot say for sure where is the right place to put my label, right? Clear? Great.
But do we know the value of k for sure?
Yes, of course, because this is in your data set.
So the k is the same for all the samples?
No, it's not. It changes from one sample to another. But as long as you can understand it, or you can do it for general T and general K, then it's going to be no problem, right?
Okay.
So every single input that you have, you can do. You can just allocate it in one specific way, right? So that sounds quite impossible, but as you do know, it's only impossible that is impossible. So we should somehow deal with it, and eventually people have done it before, right? So we can handle it. Yeah? Any questions? No questions? Okay, so maybe we have a short 5 minutes, and then we keep on with that part. So I feel like we can finish it without any jumping, so let's hope. Okay. Okay, shall we go on? Great. So now let's just first start with geniated case, right? And what is the geniated case? In this case, we assume that there exists one Gini, and the Gini tells us where the segment is. So it's going to tell us just put the first label here, second label there, last label there. Okay? Then, how can I do the training? Of course, I'm going to compare Y2 with the first label, right? I'm going to compare Y4 with the second label, Y5 with the last label, right? And I can just sum them up, correct? So I can just go over the output sequence, k different outputs I have. For every single of them, I'm going to compare that output with the corresponding output of my neural network, the label with the output of neural network, and then I sum those losses out, okay? But what about the guys who left without label? What should I do? Yeah? Maybe we can use the nearest label, like what we had in the many to one case, right? Maybe I could say, here the label is 1, here this guy was also corresponding to 1, right? So this is this guy. So this is like this. And then I do know that the label is here. So here the label is V1, which is 1. But I could say this is also a part of 1, right? So I could again label it with that particular label, correct? So I could again call it 1, but maybe this is too early, so I can just use a weight, right? Like what we did in the previous case, correct? So what I can do, I can just copy those labels behind, repeat them, and then I'm going to take everything here in this first segment, so from the very beginning of the segment towards the point where the Gini told me, and I'm going to label every single of them with V1, right? And then I compare every single output with that V1, correct? Yeah? So here, don't get confused with this notation. I have this IK, and IK is the place of label K, right? For example, here, what is I1? What is I1? What is the time instant where the first label is landing? 2, great. What is I2? 4. What is I3? 5, right? So what I'm doing, I'm getting the loss, okay? And I look at YT from the previous label, right? Or previous point where the last label was landing, to the point where my current label is landing, right? So I start, for example, from point 1, the first time index, yeah? And then I go up to this point, which is I1. Then I start from I1 plus 1 and go to I2. And then again, I start from the next one and end up at I3. Okay? So this other summation inside this guy is nothing but that repetition that you do now. Okay? So you don't need to confuse yourself. What I'm doing, the Gini told me where should be the labels. So I'm going to look at everything, every single thing within that interval from the previous label to this label to be labeled with the same label. Okay? Yeah.
In this problem, we know exactly where's the label, am I right?
No, we don't know. I told right now we assume that the Gini told me. Okay? A Gini told me, and then we're going to get rid of that Gini. Okay? But if someone tells me, then I can do this, right? So it's the same thing as the one we had before, but now we have multiple segments only. Yeah? So now the main challenge is that we don't have the Gini, right? So we really don't know what that is. But if we don't know if we don't have, I mean, what do I need here? What does Gini tell me in this whole loss function here? What are the parameters that Gini told me? IKs, perfect, yeah? IKs are the parameters that the Gini told me, right? So if I don't know, if I don't have Gini, what should I do? I'm going to learn those IKs, right? What do I mean by that? I mean that I'm going to assume a bunch of I values, right? So I'm going to say first label started at I1. I don't know where it is. I mean, I just randomly choose one, right? The second one is like here. I say this is the first label. Okay? I'm going to say randomly. I1 is 1, I2 is 2, I3 is 5. Yeah? Maybe I just use this one. And what does it mean? It means that I assume here is 1, here label is 2, and here is label again 1, right? Correct? My labels are 1 to 1. So here it's going to be 1, 2, 1. Yeah? And then anything left in between, I'm going to fill it out with a copy of the last label. So I'm going to say here is 1, here is 1. This is one choice, right? You can come up with your own choice, right? You would say, no, I'm going to put it 3. And then if you do it 3, then this means that this guy is 2. And then I copy 2 again here, right? You got it? So I am going to choose one I. And if I do know I, you do know how I can compute the loss, right? Exactly the thing we did in the previous slide, correct? So given I can compute the loss, correct? Now, I just write down my loss to be a function of everything that I don't know plus those i's, right? And I try to find the best choice of everything, including I. Deal?
I's are integers.
Yeah, we're going to deal with that. Yeah. This is the whole challenge. But you got the idea, right? So if I just choose one I, there are a bunch of choices of those I1 to Ik that I can take. And if I optimize everything, not only over the weights, but also including, I is within my parameters, then I am training everything, including the segmentation itself. Clear? So I'm learning where those I's are landing exactly. Okay? But as your friend said, I is integer, meaning that if you want to do the training, we really cannot do that, gradient computation, and then we move towards that gradient. Nothing like that happens anymore, right? So this is the whole challenge. Okay? Now, let's first look at this problem without thinking of gradient or backpropagation or anything like that, and see how we can solve it optimally. Okay? Say we are, Genie is not here anymore, but we have a very good computer, okay? A supercomputer which can do the computation within a very small fraction of a second, okay? Any computation. Then, how can I do this training optimally? Okay, I can just start with one I, okay? I start with one I, and I go ahead and train my neural network, right? Then I go for the next choice of that vector I, and again I train my neural network. I do it for all possible choices of I, okay? I have 10 different possible choices of I, okay? In this particular example, you can go ahead and count it, and it's going to be 6 different choices, right? So you can get this 1 to 1 and put it in 6 different ways here, okay? And if you do that, you start with a case 1, case 2 till case 6. And for every single of them, you are going to train your neural network. Okay? When you do the training, everything is over. Then you're going to have a training loss, right? So you have 6 different training losses after the training for every single case is over. Clear? And then which one do you take?
The one with the lowest loss.
Lowest value, exactly. So the thing that you are going to do is you are going to look at all those 6 cases, and then you take the one which is giving you the smallest possible training loss, right? And then you're going to say that that I is corresponding to the optimal segmentation. Correct?
But this
Yeah.
works because we know the value of k.
Sorry?
Okay, this works because we know the value of k.
We know the value of k, yes.
But if we don't know the value of k,
But why we shouldn't know? This is inside our data set, right? We are here talking about training. We are not doing inference yet.
okay.
Yeah? So training and then inference is going to work by its own. Yeah? So everybody, yeah? Sorry? We are going to use the same I for inference, but yes, we are going to do that. Yes. But let me just complete, and then you're going to get it by your own, okay? Yeah. Right now we're just talking about the training. But as a matter of fact, if you train your neural network to do that, then your neural network also learns to find out the optimal choice of I, right?
Like maybe the optimal I for the training side is not cannot be generalized.
The optimal I for training, yeah, it could be. I mean, this is of course more complicated learning problem as compared to the other one. I mean, it could potentially lead to worse performance, of course. That's correct. But at least given the data that you have, this is the best you could do, right? When you don't know even the segmentation, right? So everybody's clear? Great. Okay, now, do you think this is computationally feasible if we get into a real sequence? No, because the number of cases that you can get these different labels and put it in your sequence is going to exponentially grow with the length of your sequence. Now, you might say, why exponentially? I mean, just let's consider one simple, the simple example that we had here, okay? Say we had here the labels 1, 2, 1, okay? And I'm going to do something, which is a rough estimation. Don't kill me, then I explain, okay? But just wait a second for that. So 1, 2, 1 is the label every single frame could have, right? Now, this guy could be 1, 2, 1. This guy could be 1, 2, 1 till the last one, right? And then how many frames do I have? I have 5 frames, correct? So I have 5 different frames. Each of them could be labeled with one of those labels. So it's going to be 3 to power 5, correct? And then if instead of 5 you put t, then it is some number to power t. And I do know that all of you would say, here in the first one you cannot put 2. Here in the last one also you cannot put 2, right? Correct? I do agree, but they are not going to reduce the order of the cases, okay? So I don't mean really exactly 3 to power 5. For this one, this is simply 6. It is not 3 to power 5. This is obvious. But when you scale it, everything goes one number to power t, okay? When the sequence is very long, those number of cases which you exclude are going to drop, right? So there are going to be a few of them, but lots of guys in between could be every label, right? And because of that, this is going to increase exponentially with the number of the length of your sequence, okay? So what do I mean here? In general, I do know this is not 3 to power 5 here. This is, as I told you, simply 6. But you can simply do a rough calculation, and you see that it's always going to increase with the number, exponential with the number of cases. Okay? So you got the idea?
Isn't it choose k amongst?
Yeah, this is even less than that. I'm going to show it on a graph for you now, and then you're going to get it. And then you're going to agree with me that this is again exponential. Okay? Okay, but you have feeling why this is exponential. You have a very long sequence, and for every single one, you pretty much could take any of the entries inside your labels, right? Not all of them, but a fraction of them at least. And then it's going to be that fraction to the power of your time sequence. Now, let's make it more clear here for this example. Look at the outputs of your neural network, okay? So you have 5 frames. So you're going to have 5 different outputs inside your neural network. And the thing that you are going to do, you want to just put labels on each time, right? Correct? So now, what can I take as the label for the first time interval? My output sequence, my label sequence is 1, 2, 1. What should be the label for the first time interval? Can it be 2? No. What should it be? 1, right? So the first guy could be 1. It cannot be 2 and 1, the second one, right? Because, obviously you should start your sequence, correct? Right? What about the next one? What could it be? It could be 1, so it could be still 1. It could just jump to 2, right? So it could be 1 and 2, correct? Now, what about the third one? It could be still 1, the first one. It could be 2. It could be 3, right? Sorry, 1, this guy, the second one. Yeah? So it could be any of them. What about this y4? What it could be? It could be 2 or the second one, right? So it cannot be the first one anymore because my sequence is going to end at 5, yeah, right? And what about y5? What could be the label for y5? It could be the last one, right? So it could be like this, right? And you do know that, again, it's not simply multiplying them, the number of cases next to each other. Because what you would say, okay, if I start from first time interval 1 here, my next label, it could be either 1 or 2, right? But if my second label is 1, what could be the next label? What could be the label of y3? It could be again 1 or 2, correct? What if the label here is 2? It could be 2 or 1, right? Now, if I am here and my label is 1, what could be the next label? It could be only 2. It cannot be 2 or 1. Because 1 cannot be, I mean, I can label 1, 1, 1, but I should then definitely make it 2, right? So it's the only case, right? What if I am labeling here 2? What it could be? 2 or 1, right? What if I make it 1? It has to be 1, right? The sequence is ended. So now, what about the next one? I mean, it doesn't matter if it is 2 or 1. It should be definitely the last one should be 1, right? Now, how many cases you do have? It's exponential because it is the number of paths you have from input to output, right? And this is not exactly 3 to the power 5, I do know. But if I just get a very long sequence and a fixed number of labels, then you're going to see that this is going to increase. This number of paths that you have is going to increase with the length of your sequence, right? So you now agree with me that this is an exponentially hard problem? This is NP hard. You cannot easily solve it because the number of cases you have is exponential hard. You can just simply look into a very tiny sequence and then you see that the amount of time you need to search to find out what is the correct or the optimal label is more than the age of the universe. Yeah, it's impossible, right? Okay, great. So this is exponentially large. This is a very hard problem. And one key property that it has is that every particular segmentation, and by segmentation I simply mean the way that I write down this sequence, the way that I copy them. Every possible segmentation corresponds to one particular path on this graph, correct? For example, if you look at this blue graph, this is one segmentation. This segmentation says that I1 is 3, I2 is 4, I3 is 5, right? This is one segmentation. This is another segmentation, and so on, right? Correct? Everybody sees? So if you start from beginning on this graph, like this, and then you take your pen, and you just draw one line, one path towards the very end, you're going to just draw one possible segmentation. And once you're over with just completing all possible paths, then you're over with your all possible segmentations. Clear? Good? Now, this is one possible segmentation. And in general, as I told you, the number of possible segmentations that you have is exactly as large as the number of paths that you have, right? Now, what I'm going to do from now on to just make it easier even, you see, that's easy. I'm going to make it even easier. Sorry. So now, the thing that I'm going to do, I'm going to just write down the expanded label sequence. Meaning that if I am considering this segmentation, when I want to do the training, what would be my label? It's going to be, I'm going to say the first one is 1, 1, 1, and then 2, 1, right? So it's correct that the true label that I have is the sequence 1 to 1. But when I want to do the training, I'm going to just look at it as 1, 1, 1, 2, 1, right? Correct? So every single path is corresponding to one possible segmentation, and that segmentation has one expanded sequence of labels, right? And that expanded sequence of labels is of length what? What is the length? T. Exactly. Because this is giving for every single time instant one label, correct? Now, I am going to show this with V tilde LT, okay? This is a bit of, messy notation, but I simply mean that this is the label that I am giving. So here, like it is 1, 1, 1, 2, 1, but this is a label that I give when I'm moving on path L, okay? For every single time. Clear? Now, if I want to write down the same problem, the same optimization problem that we had before I write it down for you as a function of that vector I, right? But now I can write it down as a function of path L, right? And every single path is corresponding to one of those possible i's, so I really don't need I anymore, right? That's more visual, right? So every single path has its own particular loss. So it's going to be r hat of L, path L. And that is that I go over that expanded label sequence of that path. I compare every single entry here with the corresponding entry of y, the output of my RNN, and then I sum them up. Clear?
But shouldn't the weight also depend on I? Because
Yes, it could be potential, but right now you can even ignore it. Yeah, that's not really harming the whole process. So maybe for the moment you just think that weight is always 1. Yeah, but you are right. I mean, you could potentially just change the weights from one path to another. That is potentially possible. Yeah. At the end of the day, those weights are not going to really impact hugely. Yeah. Okay, so everybody's clear what I'm doing here? Now, if I want to do the optimal segmentation again, what should I do? I should go ahead, just minimize every single r hat L that I have for all possible paths, and then I find the path with minimal training loss, right? And that is my perfect path, correct? So at the end of the day, I can simply write it down in this form, and this is what, the very first case that we started with, where we had perfect segmentation. So what we have now, we have a bunch of perfectly segmented problems, and then we want to just search between them and find what is the best one, but the issue is that the number of cases we have is exponentially large. Clear? Great. So now this guy has no problem. This guy can simply be trained for one particular choice of L, because basically you can compute the gradient of your loss with respect to every single output, right? Great. So I can then write down the optimal segmentation algorithm, which is not computationally feasible, but I can just define it on this graph. So what I'm going to do, I'm going to start with my loss being infinite, so very large. So I do not have any optimal path. I do not have any optimal segmentation. Then I start with my first path on this graph. And then for that path, I'm going to go and compute the loss. And then I train my neural network with that loss for a sufficient number of epochs, right? When I do that, my neural network, my RNN, gets trained with that particular segmentation, which corresponds to path L, right? And then I'm going to compare that loss that I got after training with what I have saved up to this point, right? If that loss is smaller than what I have saved, I'm going to say this is the better path, right? So I'm going to get that new loss. I copy it at this r hat, the blue r, right? This is now the best loss I got in my training. And then the path that I have is going to be my optimal path. And I go for the next path. If in the next path I get a better training loss, I'm going to again take that loss. I say this is now my minimal loss, and corresponding path is the best path. And I keep on doing this till it's over, right? Till all the paths in this graph is over. And once it's over, I'm going to just return the optimal path. Clear? This is, yeah, just a second. This is going to be the optimal segmentation approach, the one we had with I before. Now we can write it down in terms of the graph, right? So, yeah.
If we include one segmentation, we both, for example, have 1 and 2. And you
Sorry?
know, for example, the T2.
Yes, yes, yes.
Yeah, it's going to be both 1 and 2, for
Yes,
example.
yes, yes.
Okay. How should we weight it for our loss?
You mean this weight
Yeah,
here?
exactly.
Yeah, I mean, this is a bit of challenge. I mean, you could think of, but at the end, it's not going to show up that crucially. I mean, it depends on, I mean, if I would say if k, the number of labels that you have, is a fraction of t, say even 0.1 times 1/10 of t, it's not going to be a huge impact.
Yeah.
I mean, if you put all the weights to be 1, it's the same thing, pretty much.
So both of them can be the optimal path, yeah?
But optimal path doesn't have to do anything with the weights.
For the optimal path, we want the loss.
We want the loss, yes.
Dependent on the weight.
No, the optimal path is going to tell you where to put your first label, right? So you have, your labels are 1, 2, 1, right? So if this yellow guy is the optimal path, it means that it tells you on the third frame, call it the first label, the second frame, the fourth frame, call it the second label, last frame, call it the last label, right? But it might be that this is the optimal path, right? And then allocation of the labels to that time intervals is different now, right? So this allocation of the labels to the time interval has nothing to do with those weights. I mean, those weights are, once I fix that, then I could say, okay, the label here is 1. These guys, in reality, they do not have any label, but I'm going to call it again 1. But in order to avoid, extra burden on my neural network, then I just weight the loss here and here with some factor smaller than 1. I can do that. I can simply ignore it. I can put all the w's to be 1, but it doesn't change the optimal path. Okay?
Isn't the optimal path dependent on the sequence? Like the example where the 1 can shift.
Which one?
Like when the drawing on the blackboard, the
Yes,
one
yes.
can shift.
Yeah.
And I guess it will have significant effect on the.
It has, yes, of course. I mean, it depends totally on your sequence. So we are doing it for a sequence now, yeah, right? And this is why we have a trouble. I mean, if we could just say this is the perfect segmentation for every sequence, then we could just go on with some alternative approach. But here we need to do it for every single sequence, right? So you got the idea how we do the optimal segmentation? Why this is very complicated? Now, so you might tell me that, okay, say we are going to do this infeasible training, then how we are going to use what we have trained here later on to just do the invariance, right? So if you want to do that, it was optimal segmentation. We infer labels of each segment based on its corresponding outputs. Yeah, okay, I thought I had one slide for it, but basically I have written it here. Okay, so if you want to do the invariance, when you do this guy, yeah, it's going to just give you one optimal segmentation as the output. And you can, of course, use that segmentation to just read your output, right? So when you do the training here, at the end of the day, you get L star. And once you have the L star, you do really know what is the place of the first label, second label, and third label, right? So you can do it. So here in this algorithm, you only need to just give out this L star, yeah? But the question that you might have is how we can do it in practice, since it is very complicated. And then the idea is to go ahead and use maximum likelihood approach. So anyone has heard of maximum likelihood before? Yeah? Yes. Great. So yeah. So those of you who have some background on estimation or detection theory, you do know maximum likelihood is a kind of, general approach to do that. In fact, all of the training that we have done up to this point, from very beginning, we were actually doing maximum likelihood without we knowing it. Yeah? Because those losses, empirical losses that you compute, they're actually the likelihood or logarithm of the likelihood that you would get in your for your model to have that particular output. Yeah, but just forget about what I said. Just keep it in mind. Maximum likelihood, you are somehow using. You have already used it. Yeah, but how we do the maximum likelihood segmentation. So I'm not going to just break it with the whole details. I just want to give you the general idea. So what is the general idea? The general idea is that just start with a bunch of learnable parameters. Okay, if I have a bunch of learnable parameters in my model, then I can go ahead and compute the output sequence of my RNN by a forward pass. Meaning that I get my RNN just initiated with some weights. Okay, forget about the path right now. I just compute, just give the weights to it, just some initial random weights. And then I start to give my input sequence to this RNN, right? And then at the output, I see a sequence of outputs, right? So I can do it, forward pass, over, right? When I do that, then after that, I'm going to look at the output sequence. And out of that, I do some guess about the segments, okay? How we are going to do it, I'm going to show you one simple example. Okay? But I'm going to look at y1 to yt, and then I say, okay, maybe at y3 it was the first label, over. Maybe at y4 the second label was over, and y5 was the last label. Yeah? So I look at the output, I just do one guess. That guess is probably not a very good guess, because my RNN was initiated with something random, right? But now that I got this segmentation, then I can compute the loss, right? With that bad segment, correct? So I just looked at the output, I just had one guess for segmentation, right? And then this means that I have specified one path. And once I specify the path, I can compute the loss. I compute the loss, I can do backpropagation, right? And when I do the backpropagation, I can go ahead and update my weights, right? Now that I have updated my weights, I get back here to the forward pass. Again, I do the forward pass. I generate all the sequence of the outputs. I look at them, do a better guess about the path, the optimal path. Again, compute the loss, and then do backpropagation, and repeat this over and over till everything converges. So did you get the idea how I'm doing it? Everybody's clear?
If it has converged, will it guarantee to be the output?
No, it's not. Yeah. But it's just the best thing we can do with feasible computation.
It's a hinted way to pick the optimal path.
Yes. Yeah. Okay. But good question. That this is important because we're gonna. I mean, CTC is gonna show up because this is not going to most of the time. It's not going to really lead us to the optimal segmentation. Somewhere close, not even close to that. Some sort of local minimum, which is not necessarily the good one. Yeah.
So I'm asking that because if anything that is based on some heuristic, this is based on some heuristic.
Yes.
If anything based on heuristic, then there's a way to prove that if the heuristic is good enough, then we landed up in the optimal.
Actually, this is not totally based on heuristic. The way that I presented here is the greedy way of solving the original maximum likelihood problem. Because if you want to solve the original maximum likelihood problem, that is the optimal solution again. But that one is again exponentially hard.
Okay.
Yeah. What I showed you here is the greedy way of doing it. And then greedy way, you can do it with linear complexity or polynomial complexity. But of course, there is no guarantee that you find the solution of the real maximum likelihood problem. Yeah. So everybody's clear what we're doing here? Okay, great. So just first, let's look at the pseudocode. So as I told you, I am going to just fix the number of epochs, number of iterations that I want to train my neural network with, for example. And then I start with the first iteration. I'm going to pass forward in time. And then I get the sequence of the outputs, right? So my RNN is fixed. I just look at the outputs, right? And they are a bunch of useless, pretty much useless outputs, right? But I look at those outputs, and I compute the probability of every single label in that extended label given the path, okay? And you might tell me how I can compute it out of those values of y. I'm going to show you, okay? Don't worry about that. But I'm going to compute one chance, the chance for every single path, okay? And out of those chances, I'm going to take the one which has the largest chance. Yeah? Actually, this is not the chance of every path, it's basically the likelihood of every path. Because if you sum that p over L, it's not going to be necessarily 1, right? L is in the condition, it's not in the argument, correct? So it's a likelihood in terms of L. I'm going to check the likelihood of every single sequence with respect to given the outputs. And out of that, I am going to just find the maximum, the one which has the maximum likelihood for that particular output. Okay? And then when I do that, everything is easy then. Then I am going to say, OK, L star is the one which maximizes the likelihood. I can compute the loss. I can backpropagate. I can update. And then I get back to line 2. I keep doing it till my training is over, right? And when the training is over, I'm going to return the learnable parameter, all the weights of my RNN, plus the L star, which is given by the maximum likelihood approach. Everybody's clear? Any questions? Great. OK. So you might tell me why we call it maximum likelihood. I mean, basically, as I said, this guy is likelihood of one path, right? And we are maximizing the likelihood, so this is maximum likelihood. Yeah? And then the other thing that you might say is that how I can compute that likelihood of one path, yeah, given that output y1 to yt. Okay. So let me just give you one idea. Say I want to compute, say I have done the forward pass, right? So I had my RNN fixed. I gave x1, x2 till x5. I saw y1, y2 to y5, right? And I told you that every single label here is either 1, 2, 3, 4, right? Meaning that the output of my neural network at every single time is a vector of length 4, and every single entry is the probability of that class, right? Maybe this is meaningless right now, but this is one probability, right? Okay? Now, I want to compute this probability that I have this extended. This is the probability of my extended label given the yellow path that I'm showing here. Do you have any idea how can I compute it? So this path tells me that the first label should be 1, right? What is the probability of first label being 1? No. Given the output of my neural network. So this is the path that I want to compute its probability, right? I don't know that this is really the label. I just want to know what is the chance of it. So my neural network at the very first time interval, it just returns this guy, right? What is y1, 1? Exactly. This is the probability of the class here being 1, right? What is y2, 1? Being 2, exactly. y3, 1 being 3. y4, 1 being 4, right? And now, what is the chance of this guy being the true label? Given the output of my neural network, this is not the true probability. No, it is y1, 1. I mean, my neural network tells me that looking at what you have given me, I'm telling you the chance of this guy being class 1, this segment, frame, is y1, 1, right? So I'm going to trust it. Okay?
And in the best case, this likelihood vector will be 1, 0, 0, 0, right?
In the best case, yes. In the optimal case, exactly. This is going to be, if this yellow path is the optimal path.
No. If this is not the optimal path, we should see y1, 1 to be very close to 1, the other to be 0, right? Because there's no other labels. Because it cannot be 2.
It cannot be 2. Yeah, of course. When your neural network is trained well, then no matter what, it should give you 1, 0, 0, 0. Yeah, you're right. When it's trained well, hopefully it should give you that, but it doesn't happen always, right? Because you cannot, I mean, given your computation, your resources, you cannot always perfectly train that, yeah? But if in ideal world, yes, that should be 1, 0, 0, 0. But what about this guy? Huh?
This will be the first two values will be not 0.
Yeah. Yes. In this case, in here, yes. If this guy, this yellow one, is really the optimal path, then in the ideal world that should be again 1, 0, 0, 0, right? But if your optimal path is this one, 1, 1, 2, 1, 1.
That will be 0,
1, exactly. So you get the idea, right? So if you could trust your neural network, it would have give you the correct chances, right? And then you could simply compute the likelihood by multiplying the chance of every single label in this path, right? So what do I mean? Let's look at this one. So I want to just compute the chance of this yellow path given the output that I have in my neural network. So if I want yellow path to happen, then this means that the first output should be really 1. So I'm going to get y1, 1, right? And then for the second entry, again, I want it to be classified as 1. So I'm going to get y1, 2. For the next entry, I want it to again be classified as 1. So I'm going to get y1, 3. For the next one, I want it to be classified as 2. So I'm going to write down here y2, 4, right? And then for the last one, again, I want it to be classified as 1. So it's going to be y1, 5, right?
Shouldn't it be 1, 3, 5, y 3, 5?
Sorry, y? No. This is, I mean, the index of y is your class,
Yeah.
right? So here your class is 1, 1, 1. Here is 2. Here is again 1. Yeah? So this is still 1. So it's going to be y1, 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 y2, y1. And then the numbers in the brackets are the time interval, right? Now, you can do it for this yellow path. If you have another path, if this is the other path, yeah, you can again compute it, right?
Doesn't this suppose that the tilde t are independent variables when we go from the...
Yes, of course, yes. You assume that they are independent variables, which is not necessarily the case. But given that we are doing enough amount of simplification, that is pretty much nothing. But this is completely correct. Yeah, so we are ignoring the. We are just considering IID sequence for the extended labels. Okay, so you got the idea how I can compute the likelihood, right? And I can do it for every single path. If I tell you it is 1, 1, 2, 1, 1. Then you're going to keep these two first values. Then here it's going to be y2, 3, y1, 4, y1, 4, 5, right? You just go over the path, and then you multiply the probabilities, right? Or better to look at it like this, right? So for every label, you're going to just take the corresponding probability computed by your neural network. You put it there. And when you move over your particular path, you're going to multiply everything you see on your path, right? And then that's going to be the likelihood of that path. Any other path has its own likelihood, right? And then, well, if you want to do maximum likelihood, you're going to just go ahead and find the maximum, the one which has the maximum likelihood in every iteration, yeah? But did we do any magic here? Does it reduce the complexity? What is the number of searches I should do here to find the maximum one? The same as beginning, right? So it seems that it's not going to work, yeah? But good news, you can write it down now in terms of dynamic programming. Yeah? And when you write it down, I don't know if you have heard of Viterbi algorithm, widely used in coding, decoding, yeah? And then you can just write it down and you see this is a dual problem to what you solve it with Viterbi algorithm, okay? And then you can use Viterbi algorithm to find this solution, okay? Then it is not any more complex. It's computationally efficient. Because when you move on a tree, on a graph, okay? Once you see something is more than the other, you're going to lose the track of that path, right? So if I get, initially you have a few paths, right? And they are going to increase. But at each point, once you know that one of them is larger than the others, there is no reason that you keep on with the other path, right? You're going to keep the large guys, right? So it's going to reduce hugely. And then you're going to solve it efficiently on the graph. Okay? So that can be simply solved. And then these two steps, you can basically do it by using the output of your neural network plus Viterbi algorithm, and now this is going to work, okay? Now you can solve this problem efficiently in time, okay? Everybody's clear? Great. So people got into this point, and at this point they said, okay, it should work. They started to code it, yeah? They coded this one, but it didn't really work. What was the issue? The issue was that you might say that this L star that I'm showing here is, I used to show L star with this star, yeah? And then I changed it to this star. And you might think, okay, he has done another typo, but it was not a typo. That L star, this guy, is not necessarily your optimal one because you are solving the problem iteratively, right? You're getting the output, you're predicting based on that, and then you are again going in another loop, right? So the thing that you are doing a greedy solution to a very exponentially expensive problem. And this is obvious because there is no free lunch for you, yeah? Right? When some problem is NP hard, you cannot solve it with an efficient solution, polynomial time. If you could, then you get, this. Yeah, not Nobel Prize. You get like a huge prize. Yeah, but you can leave for the, not only you, anyone after you from your family could leave for the rest of their life, right? Without doing anything, right? So, yeah, we cannot solve it really. We are just approximating it. And people started to do that, but it was not working because that greedy algorithm was getting stuck at some bad local optimum, right? It was not really moving to the best solution you get with the true maximum likelihood or with optimal segmentation. Now, people thought, okay, this is a complex problem, and by nature, it's not getting to resolve, yeah? And probably at that point of time, nobody knew, nobody who knew thermodynamics and statistical physics tried to solve this. But at some point, they started to do that, okay? And because of that, they came up with the idea of CTC algorithm. So now, I would have loved to just go over CTC, but I don't want to do it because I don't have time, and also the details are not that important for you. The key idea here, which I want to just transfer to you, is that instead of going over every single path and taking the maximum one, they thought maybe we should go ahead and compute the loss to be the average over all possible paths, right?
Isn't this like Markov chain?
No, this is not Markov chain.
Because the Markov chain, you jump from, we will jump from one path to another using the probabilities that give like the energy, I guess. And at the end, you will go to the local minimum.
You are somehow getting it right, but this is not because of the Markov chain.
Oh.
I tried to explain in the next slide, but this is a bit of more details. Those people who do thermodynamics, statistical physics, this is known that when a problem is very hard computationally, if it's a kind of average problem, you can approximate the solution, not the argument of the solution, the value of the solution, the minimum free energy of the thermodynamic system. Whereas when your problem is a marginalization in the form of maximization or minimization, which is very singular, then you cannot even approximate that. Yeah? And the whole intuition behind it is that one. But you don't need to take it complicated. You can just look at it this way. So if I compute R hat, which is the average of loss that you get over all possible paths, okay? One of those paths is your optimal path, correct? So it means that I can write it down in this form. I can say this is the loss of the optimal path times its own probability, right? Plus sum of all other paths paths and loss of all other paths times their probability. Correct? Everybody's clear? So that R hat, that average R hat that you are computing is including the optimal path as well, right? And if you go ahead and minimize that, if you are lucky, and you are usually lucky in such problems, that R hat of L star is going to dominate everything, and then the other guys are going to be a bunch of random thing moving around it. Yeah? So those chances are very small. This chance is large enough, and then basically you minimize the average. You are minimizing the optimal one. Yeah? So it's a very high-level illustration of the idea, but it is a kind of well-established fact. Okay. Now, they said, okay, to be honest, I read the paper, they do not mention statistical physics. I just say it because I know this is in statistical physics. Okay? But I guess they got the idea from there. Yeah? That, anyone who does this probably has got it from there. Okay? So what they say that, okay, instead of just going and finding the maximum guy, so before this, I was saying that my R hat is basically the one with maximum likelihood, right? I was taking the minimum R hat, right, over all possible paths. But now I'm not doing it. I'm just averaging over all possible paths, and then I just minimize this guy. Yeah? And the first question that you might say is that how I can compute this guy. Because if you pay attention, this is different from this one, right? L here is in condition. This is likelihood, correct? That other one, L is in the argument. This is probability of your path. Do you have any idea how I can get from P of y given x to P of x given y? Bayes rule, right? So you can use Bayes rule. So you can use Bayes rule to just get from that likelihood to this term. That's fine. And then you might tell me, okay, isn't that guy exponentially large again? Because again, when I want to compute this expectation, I have exponentially large number of cases where I have to sum them up, right? Again, it's an NP-hard problem, correct? But the key point is that, again, you can write it down in form of a dynamic programming problem. Again, you can do some approximation. But this time, that approximation is going to work much better as compared to the other one. Okay? So again, we are not doing any magic here. We are still dealing with a very hard problem, but we are formulating it in a different way. And this different way leads us to a better suboptimal solution. Okay? So this is the whole idea of CTC. So if you start writing it down in this form, and then you open up the terms, so you don't really need to follow these terms here. The thing that you're going to see is that at the end of the day, you can write it down in form of the summation of R, some sort of losses over time. Okay? So again, you get it in form of a sum of losses over every single time instant. And this is good because now you have the loss, you can compute the gradient. Yeah? But there is some issues here because, for example, you need to compute the gradient of one particular time output with respect to another loss at another time output, right? And this guy, by definition, if you write it down concretely, it is not 0. But this is one of the approximations we do here. We just assume that this is 0. So it's going to decouple, make it easy, right? And then when we do this, then we're just going to, do this calculation recursively. You can see that computing those gradients here again, computing the gradient of these new losses that I have written here, again, going to look like a forward-backward propagation. So again, they drive a forward pass, backward pass for this particular loss, and then everything after that